Welcome to my channel. Today we're going to be going over how to build a singly linked list. Later videos will cover doubly linked lists and then circular linked lists, since they are simple modifications from the data structures we're going to be building in this video. As a reminder, at a high level, linked lists are constructed by creating a node object and then having them point at each other. Singly linked lists are just like the Attack Titan, always moving forward towards freedom. Before starting this video, download the data structures project below and pause here until you're ready. Going into our code, let's first look at our new object, node. For now, node will have two internal values, a generic that will be our value, so we call it value, and a reference to another node, which will be our next node, so we call it next. Now, we make our constructor with both values as parameters. Next up is our getters and setters. So because this is a data structure, we're going to be a little bit more loose on our getter and setter naming. For our getters, just do variable name value and next. Our setters will be a little bit more traditional, set value and set next. Now we're 99% of the way there. Because we don't know if this node points to another node, we actually want to make a special method to handle that if check for us, so we don't need to make it a million times in our code. So this method is hasNext, which returns if next is not null or if it is. So return this.next not equals null. And that's our starter node object. And technically, that's all you need to create a singly linked list, because all a singly linked list really is a reference to the head node and then a bunch of helper methods to make life easier. So everything from here on out is going to be making more formalized definition of that helper stuff. So let's look into our new singly linked list class. It'll have a few helper variables. Int size, so we can track the number of nodes in the list without having to loop and count every time. Then let's add a node head, a node tail, and a node current, so we can always jump to the first node, the last node, and wherever we are in the list's traversal currently. Now we'll update our constructor that takes in nothing to set those three nodes to null. Add a new constructor with just one node, the head node, and another one that takes in the head, tail, and size. The last one is easy since we're just setting values, and then set current to head as a good starting point. The middle one is a little bit trickier. We'll need to set the head and the current to the head we passed in, and let's set size to 1 for now because we know there's at least one node. But to find the real size and to find the tail, we're going to have to loop through the entire linked list at least one time to set those two. So let's do node tracker equals this.current, and then while tracker.hasNext, tracker equals tracker.next, then this.size plus plus, then this.tail equals tracker outside of the loop. Okay, now we can instantiate a linked list depending on how much info we know we're starting with. Now let's get into our basic methods. Size I've already implemented for us, and then isEmpty will be a slightly updated value to return if this.head equals null, because that will always be the most accurate view of whether the list is empty or not. Then we have our getFirst, getCurrent, and getLast, which will return the corresponding nodes. So this.head.value to return the value of the node, but we then have to cast it to generic t, and then repeat that for the current and tail. This is because our node will return an object even though we want it to return type t, which is our passed in parameterized value. And now things will get a little bit trickier. We now want to move down to our hasNext method, and this method will simply call this.current.hasNext. And then how do we want to iterate through the list? Well, we need to move our current node over one and return it. So for our next method, let's do this.current equals this.current.next, and then return this.current. But wait, what if we're at the end of our linked list and we call next? Well, that's a good catch. Same as we did in our array list before, we'll throw an exception. So check at the top, if not this.hasNext, then throw new exception, and add throws exception to our method line. Okay, well what about our add and remove methods, and then our get specific index? Well, for add, we're going to have 3 versions. Add first, add, which will just add to the end, and then add at index I, which we'll insert somewhere in the middle of the list. So add first means we're going to be pointing to a new head. So we'll take in our value and put it into a new node, and then set the next node to be our current head. Now we have two more things we need to do. If our current node is the head node, that means we haven't traversed it all, so we need to move our current node to point to this new head node. And we also need to point our existing head node to be this new head node because it is the new head. Regular add is going to be the easiest. We just have to have our tail point to a new node, then set the new node as the new tail node. Add at a location is going to be our hardest. First, we need to validate I and throw an exception if it's greater than our current size. Then we need to loop from the starting node to our I-1 node. Since we're a singly linked list, we need to make sure that all of our nodes point to the correct thing, and we can't just look back a node to update its new value. We have to start from the start. So create a temp node that points to head, then loop from j equals 0 to j less than I, j++. Then in the loop, just do temp equals temp.next to move through our nodes. Now that we're at the previous node to the node we want to insert, so I-1, let's create our new node, set its value to be the passed-in value, and set its next to be temp.next, thus inserting our new node before the previous node at location I. Now we need to do temp.setNext to be the new node, which will point our I-1 node to our new I node. To show this a bit more clearly, here's an image to help. We see a few nodes and arrows, and then we take our previous node and have it say, I'm not about you, I like this node better. Change its next arrow. And then the new node says, but don't worry, I'm still about you, and then points to our old I node. Okay, now what about remove? Well, it works pretty similarly. For remove first, we're going to do node temp equals this.head. If current equals temp, this.current equals head.next, head equals head.next, and then temp.setNext equals null. Remove last. This one kind of sucks for singly linked lists because we don't have a reference to the second to last node easily accessible. So what we do is loop to the second to the last one and then point its next to null, thus removing the tail from the list. So create a temp node that points to head, loop to size -1 to get to the second to last node, then set the tail to be this new temp node and set its next node to be null, thus removing the old tail entirely. Lastly, remove at location I. This is similar to remove last, except instead of going from the start to size -1, we just go until some I value. Then we fetch the toRemove node, which is that I node, which is the one after we loop to, set our I-1 node's next value to point to the toRemove node's next node, and then the last thing we do is point the toRemove.next to null to fully put it out of the list. And again, I'm going to show this as an image just to really get the idea across. So we have our list of nodes, and then we point our I-1 next node to the one after our I node, and then we delete the pointer from our I node to the one after it. See? No longer attached. Lastly, we have getI. It contains an index of. Well, based on the add and remove work, these have become pretty trivial. Starting with getAtIndexI, first do our I-size check, otherwise throw exception, then just loop a temp node to I and return it. Index of, loop through the linked list and return I if we find the node, otherwise -1, same as last time. Contains will do the same conversion of -1 to false and 1 to true. Not too bad. But wait, we still aren't done. There are actually a good number of bugs left to even get our base cases working. First, we never modified our size, so go to our add and remove methods and increment and decrement our size variable accordingly. Next, we have a lot of edge cases we need to account for. In our add method, what happens if this is our first node? Well, we need to set our head, current, and tail as this new node, and then return because we don't have anything to attach the node to. And don't forget to include the size increment. Now, if we add at location, if I equals 0, let's just use add first and return, just to be safe we don't mess up the implementation. Next, our remove at location is also kind of spotty when I equals 0. So let's wrap this in a conditional and then just call remove first. Again, trying really hard just to be safe and use logic we know should work. But we aren't done. Our remove first is also wrong, because what if we only have one node, and that's what we're trying to remove? In that case, we also need to reset tail to also be null. Okay, now we should at least have something that mostly works. So let's go into our main method, switch our array list to our singly linked list, run it, and oh, thank God, it does still work, at least with this example. Linked lists are a lot of work, but as we continue on in our data structures world, we'll start to see why. They'll be the basis for a large number of data structures in one way or another, so the concepts you learned here will be very useful going forward. This code will also serve as a very good starting point for our doubly linked list and circularly linked list nodes in the future. So we've paid our debts now to make next week's videos a lot easier on us. And this video has turned out really long because of how much we had to do, so I'm going to sign off here and see you all in the next video. Like, subscribe, and comment below what you want to see next or topics you'd like to know more about.